Good morning, my name is Samuel Lee, and today I'll be going over the first problem of the final. Now, I'm not going to introduce the problem because you can read about it in the PDF. I'm just going to start off by asking, is this rolling without slipping? Well, in order to roll without slip, this has to hold true. Initial translational or linear velocity is 0. This means that this has to be 0, but it's not. It's omega naught. So it's rolling with slipping. These values have to be found individually then. In order to attempt doing that, we need to draw a free body diagram and keep track of all the forces so we can pinpoint acceleration, hopefully. I don't need to explain any of this, except for the fact that gravity acts on the center of mass. And normal force acts from the incline on the bottom of the disk. Because it's rolling, we just determined that it's rolling with slipping. That means it spins that way. That means it's rubbing against the incline in this direction, which means that the force of friction has to be in the other direction. Studying the y forces gives us this normal force value that we're familiar with this entire semester. However, the x direction, we find that it's this. Okay, now force of friction is equivalent to coefficient of kinetic friction times normal force. The normal force we just found here, and kinetic friction is given to us in scenario 1. Same force of kinetic friction is just mg sine theta. That's also for gravitational force in negative direction, so they cancel out and acceleration ends up being 0. If we talk about net torques, the only torque we have here is kinetic friction in the clockwise direction. If we assume this to be clockwise to be positive, that means it's negative. Now, it's because normal force, the angle between that force and the distance it is acting on is, because normal force acts towards the center of mass, so it's 0. Meanwhile, gravitational force acts on the center of mass, so that those torques are 0. And then we know that I is 1/2 mr squared. This should not be an r, this should be an angular acceleration. I got angular acceleration to be negative 2g sine theta over r, which is negative. Now if that's negative, that means that this initial angular velocity will slow down to 0, and that means that this will be satisfied because both of these values are 0. So then it will roll without slipping, and since the initial translational velocity when it begins to roll without slipping is 0, it's going to roll down the incline without slipping. Now we can use work energy theorem. I being when it begins to roll without slipping, and F being when it rolls down the incline. So then 0 is what I just said. No external work forces, even though there's static friction, because if we consider a point by particle basis, this point is stationary relative to the incline. So then it doesn't move because of static friction, so it's 0. We're told that it's placed at a height of h, and yada yada yada. This is the kinetic friction due to for an object that's rolling without slipping, and we find that because it's rolling without slipping, anyways, we find that Vf is equal to this answer, our answer to A, while B is just that divided by R because we used the rolling without slipping condition equation. And yeah, to find T, we use kinematics. Mainly, these formulas, and you can find the details about how I exactly use them in my PDF that I sent you. Just know that the math works out. Delta, and you should be good to go. Anyways, T ends up being this long thing. And while I write this down, let me talk about scenario 2. Kinetic friction coefficient is different, which means that it'll be 2. This new kinetic friction will equate to this, and our new acceleration will be mg sine of theta, which is positive, and since our initial velocity is 0, that means this is going to end up moving up the incline. However, torque is still negative, as you can see here, which means that these values will eventually meet a point where rolling without slipping condition works. When it happens, it rolls without slipping up the incline, then rolls without slipping down the incline, and then we can use work energy theorem again. You can find the velocity that the disc is at when it begins to roll without slipping in my work. But basically, I also apply kinematics, and you end up getting now there is a kinetic energy, which I said before. Don't know why it's like I shoot myself. End up getting final velocity to be this. And this with the same logic that I used in part B. Now T, you also use kinematic formulas. The only difference is now there's a new acceleration for when it rolls without slipping. To find out, we consider summing up the x forces and summing up the torques. Static friction because of rolling with slipping. Rolling without slipping, my bad. And net torque to be equivalent to this because angular acceleration is a com over r when it rolls without slipping. Then you find a com by using a system of equations, and then you end up getting a really long time, a really large answer. This thing that I'm writing down is your answer to F after you do all of that long work. Thank you for watching.